Good morning. Okay. Good morning for everybody, and then good evening for John from Calgary. So today we will have our second event. Maybe Mas Joko can pull out the presentation, Mas Joko. Okay. So on behalf of Indonesian Rock Physics Society under Hdi, we would like proudly present our second technical talk in this year 2022. We will have a topic regarding geomechanics and cell potential. The first presenter maybe we will have Dr. John from GeoSoftware from Canada, and then after that will be followed by Mas Ngurah Beni Setiawan, Ph.D. And then after that, we will have Mas Abdullah Nurhasan, Ph.D. And this event will be guided or will be moderated by Mas Paulus Allo. Next, Mas Joko. Okay. For this morning, we will have this kind of agenda. We'll have the opening that we already have done, and then I will introduce our moderator. Next, we will have a presentation from our presenter about 30 minutes, 2 minutes for the presentation, and then we'll have 10 minutes for a Q&A. And then after that, maybe we will have time if we still have something to discuss. We will have a group discussion about 15 minutes, and then we'll be end by a closing for 5 minutes. Next, Mas Joko. Okay, just to introduce our program in iRocks. So in February, we already have our first iRocks talk regarding modern rock physics and its challenges in Asia. And then in this month, in April, we will have a second iRocks talk regarding the geomechanics and cell potential. And then it will be followed by another interesting talk, I believe. And then also in this month, we will have a university reach out program. And then the special event is Hari Kartini, and then Hadi Convention. And then we will have also some workshop and some books in the next event. Next, please. Okay, this one is our flyer for Rock Physics Education Series. We will have our speaker Pak Leonard Risapali, and then Mbak Putri Wisman, and also Mas Zain Amiruddin in here. So just keep monitoring our interesting program, and then I think we will have a beneficial for our program from the iRocks for our knowledge and for our country also. Next, please. And then I will introduce our moderator for this event, for this morning, Mas Paulus Allo. He's currently working for MOECO, and then he has a master's degree in petroleum geoscience from University Brunei Darussalam. His experience is more than 20-year experience from various multinational company, both for onshore and offshore subsurface. And then his expertise is in geophysics. Without further ado, maybe I will hand over this event to Mas Allo to have interesting talk for this morning. Mas Allo, time is yours, Mas Allo.
Okay, thank you, Mas Budi. Today we will have 3 speakers. If Mas Joko can show the slides. Okay. We will have Mas Ngurah Beni Setiawan, Ph.D. He is currently a coordinator on the research and education at IATMI. That is a society for the petroleum engineer, I believe. He also has a Ph.D. from Imperial College London. Mas Ngurah Beni Setiawan has an interest in quantifying a petroleum exploration and development risk using a geomechanical analysis. And then we will also have next is Mas Abdullah Nurhasan, Ph.D. He is currently a senior geoscientist at Pertamina Hulu Rokan. He received a master's degree and Ph.D. from Colorado School of Mines. And then he has interest in seismic anisotropy and time-lapse during his various experiences as a geophysicist. And then we will also have Dr. John Pendrel. He has a PhD in geophysics from York University, Canada, and has over 43 years experience in the oil and gas industry. His interests are in inversion, geostatistics, and phase shear analysis. I think on behalf of iRocks, we also would like to thank Jimmy from GeoSoftware for connect us to Dr. John Pendrel and have him as a speaker today. Okay. Next slide. Okay. Ground rules. We would like you to turn off your microphone and video, except when you are allowed by moderator. And hopefully, when you have questions, please write it down in the chat box. You can write it down during the presentations. You don't really need to wait until the end of the presentations. And then after the presentation ended, I will read out all the questions one by one. So, and then today we are asking all of you not to take any screen capture and recording without consent from the speakers. So we really appreciate your integrity as a professionals to avoid doing this. I guess we can just start now. We will start from Dr. John Pendrel.
You want me to share my screen then?
Not yet.
We know when.
Can you try again, maybe?
Yeah.
Try now?
Yeah.
Okay. Share screen, and share.
Okay, it's coming. Yes.
Okay. It's coming.
Yeah. Okay.
And better response to problems. Right. So today, what we want is we basically have three basic questions that we're going to ask throughout these talks. The first one is why geomechanics? As we know that in drilling design, having a safe and stable mud-wet window is necessary. The way, or perhaps one of the way to know this is through geomechanical analysis, through which the stress and rock elastic and strength properties is used to model the best scenario to drill the well for a given conditions. The second question is, why do we have to compute the stress? Well, you don't have to compute the stress. We geomechanics, we do it because we can do it for you. So that is basically just a joke. The serious answer would be because stress is needed to examine the stability of a wellbore, not just for the purpose of wellbore stability, but many operations also require information regarding the stress around the wellbore. For instance, hydraulic fracturing, perforation design, completion design. And the last questions that we're going to ask today is related to a more complex problems. Now, most of the current approach that all of us basically develop is based on two basic assumptions: that the rock is isotropic and that the wellbore cross-sectional shape is a circle. And I want to challenge those two assumptions. On the left side of the screen is a photos from Auckland and Cook, published in 1998. This is basically a very the photos illustrates the dependency of hole orientation with respect to bedding planes orientation. So you see if the hole is normal to bedding, have an angle to a bedding, or completely parallel to bedding, you will have to deal with complete different risks associated with the relative orientation between the direction of the wellbore and the bedding plane. And this is relevant when we discuss shales or interbedded sands or faulted regions or fractured regions. What are the consequences if we neglect the fact that the rocks are inherently anisotropic? So we want to get a little bit of answer what might happen if we ignore that fact. Moreover, I want to also invite you to think beyond a circular wellbore. In reality, we know that wellbore shape, cross-sectional shape, is extremely irregular. That is, the question is, what if the wellbore is already damaged? You can detect this from your calipers or from your image downhole image log. For example, after you complete the section, after you drill the wellbore, can you still compute the stress? Well, again, you don't have to compute the stress, but you need to compute the stress to various purposes. But if you can compute the stress, what we want to make sure is we can compute the stress in a correct manner. So basically, the models, all models, including geomechanical models, in this case, is indicative rather than predictive. Before going deeper, I want to basically share these two statistics. One statistic states that almost 40% of non-productive time is caused by drill hole instability. The instability referred to here is the collapse of the wellbore of the borehole, which caused the drilling pipe to be pinched, logging tools that cannot be pulled, cannot be retrieved to the surface, a drill pipe and drill string that has to be disconnected because it cannot be moved. The same statistic published by Ngurah in 2010, seen is in the pie chart, illustrates that nearly 30% or more than 30% of NPT is caused by wellbore instability. On the right is a snapshot showing successful and unsuccessful wellbore in the UK continental shelf, illustrating the dependency of the required wellbore pressure to maintain stability, considering the effect of rock anisotropy, such as shales. Well, statistics like this, if translated into investment, US dollars, can reach tens of millions of dollars every year. And this is a very large number, time and investment losses for oil and gas operators, not to mention aspects of human safety. For example, if there's a kick or blowout due to the overpressure. In fact, in shale rock, which is currently very popular, the loss due to instability can reach $500 million. If we remember these fantastic numbers, the value is very large compared to the cost that must be spent to conduct geomechanics studies. When I was still working in the geomechanics, to do one wellbore stability jobs, just to give you a rough figure, the gross estimate, that only costs not more than 100K. So imagine this 100K is not even 1% of the potential loss if we ignore this sort of effect or geomechanical effect in the designing the operation. In Indonesia, I've once involved in a study to investigate the drilling issue in East Kalimantan, offshore East Kalimantan. Although it is a major field with more than 100 wells, drilling still faces challenges in the form of severe loss circulation and stuck pipe events. Sidetracks often need to be drilled, and drilling budget overruns can be quite significant. But again, why is it important? It is important because rock changes just like us, and geomechanics can give us an insight about how it will behave and what could be the consequences. For instance, In drilling, during the excavation, the in-situ stress will be redistributed around the openings in response to the excavation, through which then the stress become concentrated in the rock adjacent to the wellbore wall. In the case where the stress concentration is too large for the rock to withstand, the rock around the wellbore will fail. And to overcome this, the drilling fluid must be designed to provide sufficient hydrostatic pressure to carry some of the load previously carried by the excavated rocks. Thus, the stress concentration around the wellbore could be reduced depending on the amount of hydrostatic pressure exerted by the drilling fluid that we put inside the wellbore. So in 1979, Bradley suggested in order to understand problems related to wellbore instability, geoscientists, all of us basically, needs to have the following knowledge. The first one is the in-situ stress prior drilling of the wellbore. The second is the extra load carried by the rock, basically the stress concentration after the drilling of the wellbore. The third is the amount of pressure exerted by the drilling fluid that we put inside the wellbore to support the extra load carried by the surrounding rocks. And the last one is, of course, the rock strength characteristic. Finally, if you think about chemical interaction between the rock and the fluid, then we have to take into account the effect of drilling fluids on the strength of the rocks. So in general, factors causing wellbore stability can be classified into mechanical, chemical, or thermal effects. So once the cause of wellbore instability is recognized, remedial or preventive action can then be taken. An understanding of the basic principles underlying the whole failure can be very helpful. So in general, there are so many factors that determine the model that you want to build. This depends on how complex your problems are. Take, for example, whether you want to treat the rock as isotropic or anisotropic, like shales, whether you want to incorporate plasticity effect or assume that the rock is just elastic, which is what we normally do. All of these factors will determine the adequacy of your models. Now, coming to the questions number 2, why do we have to compute the stress? Well, because again, stress is needed to examine the stability of the wellbore, not just for the purpose of wellbore stability, but many operations also require information regarding the stress around the wellbore. Well, then once we can calculate the risk that might occur around the drill hole caused by collapsing rocks, and we understand the associated risks and the risks have been recognized, then remedial or preventive action can then be taken or designed. For example, here, I have 2 wells drilled in the same direction, in the same in-situ stress condition, but it was drilled using a different mud weight. Remember that a high mud weight will help to maintain the stability of the wellbore. In this example, it is seen that the mud weight of the one on the left is about 9.5 ppg, pounds per gallon, which is, if you look at the plot, it is more, you have more damage than those, than the second wells, same in-situ stress, same direction, hypothetical case, if you increase the amount of mud weight that you put inside the wellbore, as seen on the plot to the left. At the bottom, if you do this at every depth at the bottom, then the best or optimum strategy to drill a wellbore can be done once the in-situ stress and the mechanical properties of the rocks are available. Now, this example shows 2 scenarios of drilling strategy using 2 different mud pressure, scenario 1 and scenario 2. Of course, then the changing of the wellbore trajectory can also be done because the near wellbore stress will change accordingly if you change the wellbore trajectory. So as you may have expected, then scenario 2 will have less damage because the mud weight that we use is relatively higher than scenario 1. So these 2 examples assumes that the rock is isotropic. The next question is, what if the rock is anisotropic? Well, then the mechanism involved will be more complex, and the risk of a drill hole collapse is also higher if drilling is directed to a non-favorable orientation. If you remember my story in the previous case. The top plot in this example, it is more complex than the one before. This is an example of a wellbore that was drilled in anisotropic rock using two different mud weights. I computed the stress around it and then compare them with the strength using the Jaeger plane of weakness and also more Coulomb. So basically, I can predict the potential hole enlargement. Remember, the potential hole enlargement around the wellbore for a given condition. But this is assuming there are no further process of failure development that occurs after this. So this is just the initial failure that might occur, which is not necessarily true. Now, by knowing the potential for enlarging drill holes, then we will be able to calculate the quantitative risk based on the percentage of hole enlargement, which direction is safer, and what volume of cuttings and cavings might be produced. The intrinsic anisotropy behavior of the rocks can also influence wellbore stability in two ways, either by affecting the stress redistribution or through the rock strength anisotropy. So consequently, in view to develop a more general solution, it is necessary for the modeling, geomechanical modeling, or modeling wellbore instability in anisotropic rock to involve these two aspects. The first one is how the stress is calculated by taking into account the fact that the rock is elastically anisotropic, and the second, and also strength anisotropic, and the second is the determination of appropriate stress-related failure criteria for anisotropic rocks to predict the breakout pressure or the onset of failure. In other words, both the elastic and strength anisotropy must be taken into account in the modeling. For example, to maintain the stability of a bedding plane, as shown in this plot on the right, for a wellbore, in this case, that drilled towards a 30-degree northeast, the margin for its inclination is limited up to 15 degrees. So that is basically the blue curve here, the cross dipping with respect to the bedding. But if the wellbore azimuth is rotated towards the bedding plane up dip, the margins widens to up to about 30 degrees as shown in the plots here, right? If you compare the blue and the green, the bedding plane is the same. The only difference is that your wellbore orientation. So what it means is that you can, of course, engineer how you want to drill the wellbore, how you want to reach the target. This figure also indicates that the lowest critical bedding plane mud pressure is in the direction perpendicular to the bedding plane. So this optimum orientation is associated with the lowest shear stress acting on the given bedding plane. And the interaction of all factors involved in basically determining the onset of the bedding plane failure, as shown in the figure, is very complicated, that one cannot expect a monotonically increasing trend. As you can see here, this is not just a standard straight line, for example. Every single points, every single combinations between the inclination, azimuths, and a strength of the bedding plane, orientation of the bedding plane will dictate what would be the best strategy to penetrate the bedding or the faults or the fractures. In wellbore stability modeling, it is a common practice to assume that rocks is isotropic, even though we know that about 75% of drilling footage must deal with inherently anisotropic shale formations. Elastic properties such as Poisson's ratio and Young's modulus are reported to show directional properties. The elastic moduli could differ by about 50% when they measured normal and parallel to the bedding. In tight gas shale, for instance, the variation of the elastic moduli can be up to 400% between the vertical and horizontal directions. Several studies have also shown that the rock strength varies relative to the orientation of the planes of anisotropy and the orientation of the major principal stress, like the one you see on the screen right now, done by Ambrose Zimmerman and Roberto Juarez Rivera. In all of the cases that I've seen, it is obvious that bedding plane stability is a very complex process that general conclusions regarding the critical inclination for the plane of weakness cannot be drawn and are very case specific. Apart from the anisotropy, the next question is that we're going to ask is that what if the wellbore has been damaged? Can we still compute the stress? For instance, for hydraulic fracturing design, for completion designs. All of the models that we discussed before have neglected the actual shape of the wellbore. The fundamental assumption is that the cross-sectional hole geometry is always a perfect circle. Evaluation of an open hole wellbore stability, like open hole hydraulic fracturing completion design, may still require information regarding the near wellbore stress state. But that can only be properly done if the definition of the cross-sectional hole geometry is expanded, not only for a circular shape, because you never have this perfect circle in practice. So we have proposed a new semi-analytical method to study the stress around non-circular holes in isotropic and anisotropic materials. The method requires only the outline coordinates of the holes, the elastic moduli of the materials, and the magnitudes and direction of the far field stresses. And the proposed method has been applied for at least two purposes. The first one is all the plots at the top, to model the episodic borehole breakout development to track the stress evolution around the breakout. You see this cartoon on the right, how the breakout developed until it reaches the stable position. So basically to model the episodic borehole breakout, we can then track the evolution around the breakout geometry, and to investigate the possibility of estimating the in-situ stress state based on the observation of breakout geometry. The method has also been used to compute the near wellbore stress around the damaged wellbore whose geometry is obtained from ultrasonic data, for example. So in geomechanics, perhaps the most important questions to ask at this stage is whether or not the breakout geometry, like the one you see at the top figures, can be used to infer the magnitude of the in-situ stresses. So what we have tried by rearranging the standard MOECO or more Coulomb failure criteria, the critical limit at which shear failure occurs can be represented what we call the MOECO or more Coulomb failure functions. That is the y-axis that you see in these two plots at the bottom. From the bottom plot, although the correlation with the maximum horizontal stress is implicit, basically you don't see that here explicitly. It is in that in the form of mathematical expression, the relation with the maximum horizontal stress is somewhat hidden within, so to speak, the complicated failure function formulation. It is still conceivable then if that the magnitude of the maximum horizontal stress can be estimated as long as, or if the magnitude of the vertical stress, the minimum horizontal stress, and the Coulomb strength parameters, basically the cohesion and the internal friction, are known. In other words, if the relationship between the breakout geometry, that is the depth or the width, is known, and the failure function is known, and if the magnitude of the overburden and the minimum horizontal stress are also known, then for a given rock strength, the maximum in situ stress can theoretically be inferred. Oops. So this is the last slide that I have for today, and we can always discuss after this. With the method that we propose, in addition to the breakout modeling that you've seen before and the in situ stress estimation, we have also investigated another potential utilization. This is something that is closely relevant to geophysicists like most of you. Another potential utilization of ultrasonic data is to obtain the in-plane near wellbore stress around the wellbore circumferences. In addition to the standard geomechanical properties, such as the in situ stress and the rock mechanical properties, the potential benefits of an ultrasonic data can be further leveraged. The first one is to provide an accurate near wellbore stress computation without making any assumption regarding the wellbore geometry, that is a perfect circle, and to serve as an input for various post-drill wellbore operations such as hydraulic fracturing, cementing, perforation, where detailed knowledge about the near wellbore stress is crucial. So we anticipate that the result could potentially improve a various design that requires the knowledge of near wellbore stresses. So basically the tangential stress, if you look at this plot at the bottom, the tangential stress around the wellbore corresponds not only with the relative orientation of the in situ stress, but also the cross-sectional geometry of the wellbore. So we don't make any assumption regarding the wellbore geometry. So detailed analysis on the tangential stress around the wellbore indicates that if you look at this plot again, the percentage difference of the maximum tangential stress, that is this red curve, may reach up to 50% with that of the standard solution, meaning if we assume the rocks is a perfect circle, which is not the case. This is mainly due to the influence of the whole geometry, which cannot be captured if we use a standard equation such as Kirch's equations. Similarly, the difference of the minimum tangential stress is also substantial. That is approximately about 25% with a maximum of 50% over a certain intervals. So some of the plots and discussions that I've shared since the beginning is taken from these references. If you are interested to learn more or to know more, I would encourage to read directly from the listed publications. And of course, then we can always have a detailed discussion offline. So with that, I want to conclude. I hope this is not even 15 minutes or not more than 20 minutes, Bang Paulus, Allo. With that, I want to conclude my talks and again, thank iRocks community, Himpunan Ahli Geofisika Indonesia, and all supporting teams to make this a productive weekend, at least for me. There's only one extra thing that I want to share, and this is what I've been independently doing in the past years. If you look at this plot on the left hand side of the screen, all of those results that are shared since the beginning require data set that is extremely difficult to acquire, let alone expensive. Uncertainty in characterizing subsurface properties may arise from various sources of measurements and empirical formulae from which the parameters are derived. What it means is that incorporating uncertainty becomes crucial in many engineering design for risk quantification based on probability of event occurrence. In these examples, I'm trying to now acknowledge the fact that rocks properties is not just a single values, but rather a distribution. It has some mean values, it has some minimum values, it has some maximum probable values, right? And what we want to do now is acknowledge that, incorporate that, and use that and in the design for wellbore stability, fracturing design, sanding, completion designs. So finally, I just want to repeat what George Box once said. He says that all models are basically wrong, but some are useful. Even the best models of the world are imperfect, right? And this insight is important to remember if we want to learn how to make decisions and take actions on a daily basis. George Box basically his point was that we should focus more on whether models or something can be applied to everyday life in a useful manner rather than debating endlessly if a model is correct in all cases or not. If you know Yuval Noah Harari, he also says that we, all of us, basically scientists, generally agree that no theory is 100% correct. So the real test of a knowledge is not truth, but utility, right? And science gives us that power. And the more useful that power, the better the science. So in summary, if you think that your seismic data, because most of you are geophysicists, and this is Hdi, if you think that your seismic data in petroleum application is only for reservoir characterization, like searching for targets, locate faults, sweet spots, high porosity, well, you have to think again. Your seismic can do a lot more than that. This is why we have Dr. Abdullah Nurhasan and also Dr. John Pendrel here with us today. With that, thank you so much, and Paulus and everyone for listening. And the screen and the stage is now back to you, Paulus.
Okay, thank you, Mas Beni, for the presentations. We have one question now from Mas Budi Permana. I think I would like to rephrase that question. So what the question is, what will be the explanation that in one field, in a field, there are several stress directions? I mean, if it's one stress direction, this easy to understand, right? But what would be the explanation if one area has a different stress direction?
Oh, well, I think I want to address this this way. Stress is influenced by topography as well, and any discontinuity that you have in the fields on any materials. Basically, this is, we are dealing not with homogeneous kind of materials. Everything in reality is very complex. So all of that topography differences, different in elastic property from one locations to the adjacent locations to the next location, will all affect not just the directions but also the magnitude of the stresses. Let alone in the fields. If you because we are talking about scale here, if you can have the ability to zoom into the near wellbore wall, then you will see that even in the scale of wellbore, you will see that stress direction can change. The presence of microfractures, for instance, will certainly reorient the stresses that you have in that particular points. So it depends only on the mechanical behavior, mechanical characteristic of the material at any scales, I would say.
Okay.
So for that reason, I think this is a very important questions, and I've observed this a lot. Then stress cannot be, I mean, stress has to be computed. Stress cannot be derived statistically. Stress cannot, we cannot get stress through geostatistics, for instance, because in order for us to compute stress, then we have to at least satisfy 6 elastoplastic or elastoelasticity equations from boundary conditions, stress strain relations, and their Formore's equation. So we cannot get stress but simply by getting, for instance, the Young's modulus from the seismic inversion, getting the Poisson's ratio from the seismic inversion, and then boom, we can compute stress just by plus minus division and all that, without then doing a proper way of getting the stress through. For instance, one of the way is finite elements, because then you can integrate this difference in material properties, this difference in the geometry, topography of the layers that is under investigation.
Okay. There are some questions in the chat box at the moment. I think we will hold that questions now and move to the next speakers. Hopefully, we will have some time for a group discussion, and then we will read out again the unanswered questions during that time. Okay. So the next speakers will be Mas Abdullah Nurhasan, Ph.D. If you could share the presentation. Mas Abdullah.
Yes, Bang.
Okay.
Paulus, I'm sorry, because I was disconnected just now and I just rejoined, so I wasn't a co-host previously. So now I
Okay.
can share and you can see my slide, correct?
Yes, now we can see your slides. So I
Can you
think,
confirm that you hear me clearly?
yes, I think we can hear you clearly. So the time is yours, Mas Abdullah.
Okay, thank you. Assalamualaikum warahmatullahi wabarakatuh. Good morning, everyone. Good evening, John Pendrel, Dr. John Pendrel. The benefit of speaking in class that some of the speaker already mentioned, already explained some of the theory that you want to explain in your presentation. So I thank you, John Pendrel and Dr. and Beni for making my job easier. So I'm going to focus in my presentation about the seismic anisotropy and how it helps crack shale's potential. So in shale oil and gas exploration and exploitation, we have several steps. In summary, we first identify how do we get the analog literature, and then geomechanical geochemistry model, how much kerogen that we have and how much kerogen that we can extract, test, examine, predict, and the first drilling and predict how the geological behavior of the well, and then how we can predict the fracture behavior, and after we extract, how we monitor the production, how we monitor the rock behavior throughout production, and how we can enhance. So in this, some of the stages, some of the seismic can help, and we can see it in the later slides. So first, Dr. John Pendrel has already mentioned about the Barnett. So here's the other shale analog play. They are all thick reservoir, high POC, and then low porosity and very low permeability and high pressure. So let's see if we can detect all of these properties and make it useful using our seismic. So shale hydrocarbon shale reservoir, is it actually shale? Well,
sorry, Mas Abdullah. Have you
yes.
put in the slide presentation, slide mode?
Oh, wait. Yes.
We still see your PowerPoint window.
Okay. How do we? Okay, I'm going to stop sharing. I'm going to reshare again. And okay, do you now see my?
It's still the PowerPoint window, not yet the slide show display. Maybe change the screen. No, not yet. That's still the same.
Okay, but you can see my.
We can see your slide here. It's just not
Yes.
big enough, I guess.
Okay, I don't know what to do. Do you have any suggestion, Bang Paulus?
Can you
Display
click on
session?
slideshow at the top there? Just click on slideshow. I can see it. In the
Yes,
orange bar.
I already show that, and I already clicked that, and now I'm showing in my screen. I'm showing the display screen or the slideshow screen, but apparently in the Zoom.
Big enough to see anyway, so no worries.
Do you see it changing slides or pages, Bang Paulus?
Yes. Oh, yes. Yes. It's fine.
Okay.
Yes.
Yeah. That's okay.
I'm so sorry about this technicality.
Now
I
we can
haven't
see it
used.
fine, so there's
Yeah.
no problem.
Okay.
Okay. Okay, let me do this so I can do that, and then okay. So yeah, now I'm in slide 4. So they are not your usual shale. So Dr. John Pendrel already shows you that we need the high quartz or V quartz, and two of the example of the other field, the Eagle Ford and the Niobrara in Denver Basin, shows that it also has a large carbonate content. So we don't have, or we can't have a pure shale in our in our unconventional reservoir, because if we do, 100% shale cannot be fracked. Dr. John Pendrel already shows the model, and so the sum of the equation for shales might not be applicable. In this case, is the pore pressure that I will show you in a couple of next slides. So in the steps of the identification, I will show you two of the method. First, I want to show the high pore pressure identification using velocity model, and also the kerogen detection using AVO and anisotropy analysis. First, this is the example from the Niobrara formation. The purpose of this slide is to show you how I predict the pore pressure difference in the Niobrara using first the Eaton equation, and how I modify the Eaton constant, or not modify, because you know, Eaton is Eaton constant. Eaton constant can vary from 1 to several values, but we usually use just the default of 2. The default of 2 only apply in shale and pure shale, and in this calculation, we already know that we cannot use the Eaton constant for our shale pressure calculation, and this even in the case of the pressure difference is equal to the effective pressure. So what is effective pressure? Not what if differential pressure. So the differential pressure is just when we subtract the confining pressure with the pore pressure without the Biot constant. If we apply the Biot constant, it becomes the effective pressure. So whenever Biot constant is not 1, so it no longer the differential pressure. So it becomes the effective pressure, which is not as simple as we thought. And Biot constant 1 is only applicable when the shale is in 40% porosity. So 40% porosity is in shale is only in the Gulf of Mexico, I guess. So I think I encourage us, if we play with the shale with the shale reservoir or unconventional reservoir, we cannot use the default equation, because we might not be able to predict the pore pressure correctly. So here we are, if the Biot constant vary, we have a variation of the pressure difference, if the velocity change 6%, we might have 25% change in pore pressure. We might have 19% change in pore pressure. We might have 21% in change in pore pressure according to what bio constant that we use. So this is my take of the pore pressure analysis when we first identified the potential of the shale hydrocarbon. And next, I'm going to talk about the seismic anisotropy, something that we needed. It's always there, but sometimes we don't want to deal with it. For example, it's a hockey stick effect in the far offset. Sometimes after 35 degree, we just mute the gather and then stack it, and then we get a very good stack. So we forgot about the anisotropy. Sinusoidal pattern in 3D gather. If we have a coca gather, before we stack it, we just trim static, apply the trim static, and then we neglect the anisotropy. But in this case, I will show you that if we don't neglect, if we use and utilize the anisotropy, we can get something useful and beneficial. So what is anisotropy? Basically, using velocity is the easiest way to explain anisotropy. It's just the different value in different direction. So if we have a laminated layer here and we have something soft in this area, in this layer, it make the velocity in the vertical direction slower than the velocity in the horizontal direction. So that's already anisotropy, and we can calculate and model the anisotropy using this equation from Ilya Sonkin. And you can see the vertical velocity in this model here, the near vertical is the slowest velocity, and the more we approach the horizontal plane in 60 degree, we have the highest velocity. So that is the anisotropy velocity model. So equation, yeah, I previously have the animation in this slide. That's okay. So Mas Sakti told me not to give a lecture, just give a talk. So I want to encourage people that we don't have to be scared to the anisotropy equation. So if you look carefully, this is the top equation, is the general equation that we use to calculate the reflectivity. It's very simple, just the difference in the summation of the P impedance. We use it all the time. We use it from maybe the first years of the college, so everybody knows that. The second one also, it's quite simple. It's just the general AVO equation. So the first term will be the intercept, and the second term will be the gradient. So that's simple. We use it also all the time, especially when we use the AVO analysis. Every time we have a 3D volume, we might go for AVO right away. So we use it all the time, even we realize it or not. So the anisotropy reflectivity on the Hdi medium, we can see it's very similar from the second equation. We just put a tiny modification, put just the one delta and one epsilon parameter in the second term, and then boom, we have the equation for the anisotropy. So it's not that complicated. It's not that scary. I try to start from the simplest instead of start from the Zupret equation. So people will see that okay, we actually can approach the anisotropy parameter and see what happened and what we can benefit from. So I take this picture from Colin Sayers and friends paper in the AGE papers. It shows that if we have more kerogen fill these layers of shales, it will increase the anisotropy. How does increase the anisotropy? Because when the kerogen more than 8% or 8% here, the vertical velocity will become very, very slow. then the reflectivity will be greater. Reflectivity greater is can be high negative or high positive. So in this case, it has high negative. So greater reflectivity, but because the velocity in this direction, in the horizontal direction, is not that changed, so still fast enough. So so the gradient become larger, and the intercept become greater compared to the one that we don't have any kerogen. Is not have that great of the intercept. Is not and the slope is not that good. It's not that great on the gradient. So just like that, we already used the anisotropy, and we already can derive how much kerogen or predict how much kerogen we have in this in our reservoir. So in the second stage, how we first we test and predict. I will use the AVAZ for vertical fracture identification and characterization. So I can map the fractures and then predict where will the fracturing fluid goes and how we can produce properly. So we already see these equations, just the fourth one. The fourth one, it's actually the third one, but we just give another modification and term. So from equation 1, 2, 3, 4 is just adding a little bit more parameter, But if we realize that it's actually just an AVO parameter, modified AVO parameter, so we don't always panic when we see the anisotropy equations. So this is the model of the Hdi medium. Hdi medium is just a VTI medium tilt 90 degree. So instead of have the slowest velocity in the vertical direction, now we have the slowest velocity in the horizontal direction. So this medium can mimic if we have the vertical fracture sets that we have in our rock. And we see here that the azimuth, the velocity is changed with azimuth. And if we see the orthorhombic medium means that it's the combination between Hdi and VTI. Now, instead of one, we have two slow velocity, slow 1 and slow 2, and the faster one will be in this direction. So this is the velocity model, and this is the reflectivity model. Basically, it's the same as the velocity. We have the highest velocity or highest reflectivity in the isotropy plane. Isotropy plane is, if I can go back here, isotropy plane is when the plane is parallel to our fastest plane or fastest orientation. And the one that is perpendicular to the fastest plane is the symmetry plane. So we have the fastest plane or the isotropy plane and the slowest plane, the symmetry plane. So here we can also see where our isotropy plane is and where our symmetry plane is. Because we are using hot rock, this is a carbonate-rich shale hydrocarbon reservoir. So the isotropy plane will be the hardest, and the symmetry plane will be the softest, creating the highest reflectivity and lower reflectivity in the symmetry plane. So in the real data, we can also compare that with the model. This is the real data from the Niobrara formation, and I put 3 angles, 20, 25, and 30, and we can see the model is similar. The data is similar with the model. We can predict or interpret the isotropy plane or where the fracture oriented, and we can see the symmetry plane, and we can also calculate the gradient. The gradient in in the FVAZ is not the gradient of the offset or along the offset, but the gradient along the azimuth. So it's the comparison between the highest reflectivity and the lowest reflectivity. So in other term, in the physical term, it's how much different the velocity or the hardness in the isotropy plane compared to the symmetry plane. So using this, we can also predict where the fracture oriented and how big the fracture affected our velocity and impedance. This is the example for the strong anisotropy medium or data, and this is if we have low anisotropy, we see that the data have low slope. The difference between the highest and the lowest is not that difference. And this is if we put it in the map. So the arrows point to the isotropic plane or the fracture orientation, and the color shows how much anisotropy we have in that area. We can predict that the if we have a big anisotropy, it means that the fracture is open, or fracture is filled with hydrocarbon, or fracture filled with kerogen. Anything that can slow down the velocity, we can assume that. So this slide show also the like a more geomechanical map of using 3D seismic. So this is a very interesting way to utilize our seismic to predict the geomechanical characteristic of the area. So after we know if we have kerogen, if we have enough fracture to be the storage for our hydrocarbon, now we can model the dynamic geomechanical model if we have a time-lapse seismic. When I study this, I was blessed that I have a time-lapse seismic. So what I did is I analyzed how much the fracturing job affect the fracture set in our area. So they shoot the seismic before fracturing, do the fracturing job, and then shoot the seismic after the fracturing, so we can see which fracture set is affected by the fracturing. So what do we expect to see when we fracture? When we frac the reservoir, we hope we see increase in anisotropy because the frac fluid filled the gap between the frac and decrease the velocity or the horizontal velocity or velocity in the symmetry plane. And is it proven in our area? Yes. This is the example where we have low anisotropy, and then after the fracking we have a mild anisotropy. See that the velocity or the reflectivity in the symmetry plane decrease, meaning that it becomes slower. Because the frac fluid has filled the fracture and make it slower. This is the other place. First we have low anisotropy, and then now we have mild anisotropy or medium anisotropy, where the amplitude in the symmetry plane become lower, indicating that the velocity in this area is becomes slower. To compare on the map, this is first the baseline or before fracking. This is after fracking, before fracking, after fracking. So it's easier if I give you the example of the difference. So this is the difference of the anisotropy So some changes is the positive anisotropy, meaning that it or increase anisotropy because the frac fluid filled the fracture, meaning that the sum of the fracking did a very good job. Maybe here we don't have a good result. So it's very good analysis for the for monitoring our fracturing and production. Pak Paulus, do I still have time?
Yes, Mas Abdullah, maybe 5 minutes.
Okay, so hopefully I can explain it quite clearly in that very short presentation. Some other methods that we can use but require additional acquisition is microseismic monitoring and shear wave analysis. So this is the layout of the wells. We have 11 horizontal wells. They have multiple stage fracking. So these are the event of the fracking that can be recorded. So they inject the fluid and then hopefully they frac. So whenever the rock frac, it creates an event, a seismic event. Small, because that's why they call it microseismic, but somehow it's recordable, and we can see how the event is oriented along the maximum horizontal stress. So this looks like a life scale geomechanical lab. Mas Beni might love this operation. So we can see that the event is oriented along the maximum horizontal stress, meaning that all the fracture that is open up, it's parallel with the maximum horizontal stress. And with this help, the reservoir engineer can predict how much the increase in the permeability that induced using the fracturing job. So the second alternative method is the shear wave. It's a very useful data, but not very common because it's still more expensive to acquire. Shear wave travel in the same direction as the P wave, but in the different polarization. It's always perpendicular, perpendicular with the direction of the propagation, and that's why we always have two type of S wave. So here we can see the vertical S wave, and here we can have the horizontal S wave, the vertical S wave and horizontal S wave. So what does that do? So whenever we have the shear wave that propagate parallel to the fracture, it became the fast shear wave. And whenever we have shear wave that propagate perpendicular to the vertical fracture, it becomes slow. So here in this gather, now we can see the slow S wave, the slow S wave, and the fast S wave. Just like that, we know we can know the orientation of the fracture, and also the how big is the fracture is. The benefit of using shear wave is that we don't need too large of an offset, because it doesn't have to go around. It just goes straight to the fractures using two orientation or two polarization, the parallel and the perpendicular to the fractures. So many methods that I showed you in the previous slides, we already have it. Most common, we already have it. We just need to know how to utilize it to actually crack our shell's potential. Some of the method like microseismic and S wave might not be available in right now, but hopefully we can also acquire that to get better understanding for our fractured reservoir. So that's it for me. Thank you for listening, and thank you for being with us in this morning. And we'll give the time back to Pak Paulus. Thank you, Pak Paulus.
Okay, thank you, Mas Agus, Mas Abdullah, sorry, for the presentations. I think with the time that we have now, I think we will continue with the group discussion. So we will try to read again the unanswered questions, and then we will ask our speakers to give the answers to that. So I think I would like to start from maybe from the Masa Duandari. He has a questions that how to determine shale hydrocarbon play for the future geological carbon storage. I think what part what he would like to ask is how do we know that we have a good potential for the shale play based on the data that we have at the moment. Any speakers like to have a take on that one? Maybe Dr. John?
You mentioned hydrocarbon CO2 storage. I think I heard you say.
Yeah, I think you would like to also mention how to make it sustain. I think.
Yeah, it's a big deal where I'm from, and yeah, my son actually works for a company that is involved in doing that, and certainly the competency of the rock is paramount. So the CO2 is put in under pressure, and how much pressure can you put in that reservoir before the rock breaks down and you lose the container. So facies are important, but the competency of the rock and the stresses that it can handle are important. So I haven't been doing too much of that myself, but I'm just starting to get interested in it, following the work of Colin Sayers and others. Yeah, so I think a lot of what we do, a lot of what I said and other speakers said today is relevant for that. Yeah, looking for a good example to try it on, actually.
Okay, and then another questions related with geomechanics, I think. Maybe from Gilang Alfian. So his question is, could we assume our well will be stable or unstable based on stress direction and azimuth well survey? Mas Beni?
Yeah, I think I've replied that also through the chat. I think the best way is to really compute the stability. Because then you can take into account not only the stress direction but also the relative orientation between wellbore and the in-situ stress directions. You can also take into account the rock strength properties and perhaps the elastic properties if you are dealing with shales, for instance, that has a tendency to behave anisotropically.
Okay. So when it comes to the geomechanics, what would be the ideal list of data sets needed?
Well, we are very data hungry. Basically, geomechanics. We want everything from geoscience to engineering design. But of course, I think Mas Sakti asked this online. Most of the cases, for instance, in exploration, what we have is only seismic data. I've worked once 15 years ago where we were asked to designed a mudwet window for a deep water exploration Sulawesi, where the closest well was 100 kilometers away. So we did not have options. But again, this is where perhaps a non-deterministic or probabilistic method would be very beneficial, in which you can basically take into account or do the modeling, not pushing the models to take a single values, but rather a combination of values and possibility through probabilistic approach.
Okay. All right.
Yeah, I would agree. I would agree with that. Everything we do these days, we want to hang an uncertainty onto it. So
Yeah.
we love Bayes and its ability to give us uncertainties on everything we measure. And I think we have to do that. And I think the industry is demanding that also.
Yeah, I agree.
Okay. Another questions from Mas Ander. So this is quite a long one. Basically, he mentioned that during the formation of oil and gas, a large fluid pressure will be generated, and then these pressures will create fractures which allow the oil and gas to escape. And then later on, these fractures may subsequently sealed by mineral depositions. So how do we identify fractures or cracks on the shale rocks using seismic data? Or maybe can we distinguish between sealing and leaking cracks? Maybe Mas Abdullah like to take that one?
Yes. Thank you for the question, Mas Andar and Bang Paulus. So basically, the method is just what I has explained. We use any seismic method that can predict any lateral variation or predict the crack within the medium. Whether it's the FAZ or the shear wave splitting, we can use that. And for the horizontal fracking that or that cause when the bitumen crack, we can also use the AVU, just like Colin Sayers did in the paper. If we want to distinguish between the sealing or leaking, sealing meaning I will assume the sealing meaning the fracture is not filled with minerals instead of filled with hydrocarbon or with fluid. I mean the leaking, sealing is the filled with mineral, right? So if we can have any reference how much the mineral changed the anisotropy and how much the fluid changed the anisotropy, so we can distinguish that. So that's why in the second steps that I shown you in the PowerPoint, sometimes we drill and get a lot of core data and see how the fractures behave, and if the fracture is not there, we can frac it in the lab, something like that. So yes, that's a lot of works, but you can also get it from the references. We already have many reservoir, many shale reservoir throughout the world. So yes, if we know how much the mineral changed the anisotropy and how much the fluid changed the anisotropy, so we do have references for the value of that.
I wonder if there's facies changes above a leaking fault that might be detected by changes in elastic properties. I've not done it, but you would think that in the old days we had zones of disturbance. That was before inversions, and there was just poor signal to noise in areas above a leaking fault, gas chimneys and that sort of thing.
Okay. I think I have raised most of the questions. Okay. One question from Mas Budi Permana. he was asking about how accurate the seismic inversion in defining the kerogen content. Maybe Dr. John would like to speak from your experience.
Yeah, in 2014, I would have showed you the slide I showed you, which it had my kerogen estimate with the wells on top, and would have asked you to compare the wells to the kerogen estimate and get a gut feeling of whether it was a good match or a bad match. But in 2022, now getting into what we call facies-driven modeling, we actually want to, in addition to making those kerogen estimates, actually put out a standard deviation volume. And this is because we're using the Bayesian techniques. And our probability density functions that we use, they have means, but they also have standard deviations. That standard deviation tells us about the uncertainty we have in the probability. So we can run some simulations of kerogen or whatever we're estimating using not the mean probability, but we can go one standard deviation either way. We might have 5 or 6 or 7 or 8 different facies. Each of them can have a PDF that has a standard deviation. So we have many combinations of possibilities. We run them all and then look at the standard deviation of that set of answers and then put that out as a volume. So we've tried that in a couple of data sets and we like the results. So we're going to see how that goes. But that's our present thinking, is to try and formalize that just a little bit better. And when the facies are not very indicative of a property, maybe like permeability or something like that, then we hope that standard deviation can be very large. And when it's something like V clay or water saturation, that it would be smaller. So that's our approach.
Okay. I think next I would like to go back to Mas Beni. So you have a lot of experience here with the geomechanical analysis. From your experience, can you share to us what kind of what would be the indications, or how do you know if a certain geomechanical analysis done wrongly? You know the correct way, right? But how can we spot that this is wrong from your experience, maybe?
I did a lot of mistakes in the past, basically, but I think of course I mean one of the examples is stress predictions. I think Mas Abdullah and John knows this very well. All models are basically wrong, but probably a few of them are close to the actual measurements. Like you do hydraulic fracturings, you get the closure pressure, and then you know how far you are off from the actual measurement. And then from that point, what's more important is the flexibility that you have and the capability of the models to mimic the actual conditions. And then you have to update the models accordingly with more and more data that you have on the tables. I think that would be my response from someone who did a lot of mistake in predicting stress and then strategy in drilling as well.
So any advice on what needs to be checked before we are confident?
This has nothing to do with methodology. I think everything is quite standard. This has nothing to do with data set because we don't have sometimes the luxury to have all the data that we need. But I think what I've seen is this is all about mindset. People always think that, for instance, the shear sonic is very rare, right? And even though when you have sonic data, you process the sonic data only up to get the standard products. So this is about mindset, that if you think those data as an investment rather than a cost, then you basically can get a lot of information out of it. And geomechanics is basically a discipline that is integrated, like one of the slides that I showed you before. And most of the answer or the moment of truth of geomechanics comes from, for instance, advanced sonic processing. like the dipole sonic processing, where you know where the damage is behind the wellbore wall, not only at the wellbore wall. You can detect the plasticity behavior behind the wellbore wall, and then you can sort of predict the onset of damage, or the damage before they actually captured by the image log, for instance, which is basically very sensitive sonic can detect that very sensitive things that you can get only if you invest in your data, Mas Paulus. I think the tip is really to change the mindset. The data that you already have will, I think, can do a lot more than what you might think it can be doing at with a standard processing only.
Okay. Next, there is a questions from Pak Theo to Mas Abdullah. His questions is for the application, could we determine its sequence of petroleum expulsion fracturing by anisotropic and reflectivity AVO analysis? So if you can take on that one, Mas Abdullah.
Yes, Pak Theo, thanks for the question. So basically we can, but again, it's better if we have the not the model, if we have the data from the lab, the reference data from the lab, and how much the expulsion of the hydrocarbon affect the anisotropy. So whether we have the actual data from the wellbore, or we can get any shales, and then we put it in the lab. We inject fluid inside, and how much see how the expulsion can crack the rock, and then we can measure the velocity to measure the anisotropy that caused by the expulsion. Maybe that's the answer, Bang Paulus.
Okay. Okay. I think I would like to remind everybody to fill in the attendance list as well, because usually the secretariat would like to do some graph analysis. We would like to reach out as many people as possible. So I think if you could fill in, it's very appreciated. I think maybe next one, I would like to go to Dr. John Pendrel again. You mentioned about that phases-driven version in your presentation. Is that something similar with the where you jointly invert the impedance and phases, or is it something different? Or not to mention specific products, but I think
no. I took all the brand names out of my talk. I hope I got them all. It took me quite a while. Yeah, the idea of creating that algorithm was first. It was driven by the idea that we needed better low frequency models for inversions. And so typically, traditionally, low frequency models from inversions are not what we call data driven. They're interpolation between well logs. And you can have triangular, nearest neighbor, exponential, kriging, whatever you do, as to quote someone else, you know you're doing the wrong thing. And so we've been interested over the years in data-driven approaches and data-driven by attributes. We have a process that does that. The idea was that if we have done a first pass of inversion and got some facies estimates, and we know the properties, the reservoir properties, P impedance, VBVS, and density of those facies, then can we make a data-driven model that's driven by facies? And if we can make that has some variability between wells that really has some meaning, and then we can feed that back into another passive inversion, use the low frequencies, it would be a better low frequency. And so we did a paper in the leading edge there in 2020 and showed that we got better accuracy by doing that procedure. And so we proceeded to create formally an algorithm, an application that would do that easily. And then sort of accidentally discovered that you could estimate more than just P impedance and VPVS and density. Even using facies that were designed from P impedance, VPVS, and density, you could ask the question, do these facies speak to us about other things like porosity, V shale, water saturation, V clay? And you can look at cross plots and answer that question. Yes, they do. No, they don't. And if they do, then you can model those properties. And of course, what we discovered is that the goodness of the relationship is not uniform across the project. It varies with the facies itself, and it varies laterally. So we get standard deviations in one section of the project, not in others, higher, not lower. It changes all over the place. And we thought, well, this is very interesting. We can do other reservoir properties. And pore pressure was mentioned by one of the speakers, the Eaton method, but Wernick, for instance, has a method where he needs V clay and takes into V clay effects. And we heard how Kerogen, in fact, can affect VTI tonight or this morning or wherever you are. And so these properties become important now, V clay and Kerogen, for like pore pressure sort of thing. So when we discovered that it had other uses, it sort of opened up a whole bunch of ideas and potential and direction that we want to pursue now. But the original reason was to make low frequency models for inversion. That's why we did it. But it looks like it has more potential than that, really. So that's nice. And we're just sort of beginning on this and going to publish our first paper in June.
We have another questions from Trisakti. I think we can take it as the last questions, I think. So his question is, how many direction of seismic azimuth in order to efficiently solve the AVAZ, the amplitude versus azimuth, or VVAZ analysis? In particular, if we refer to Ruger approach, for instance. Any thought, Dr. John or Mas Abdullah? Mas Abdullah, you want to take that one?
Well, instead of minimum efficiently maybe 0 to 180 degree, meaning that we acknowledge the reciprocity. So we only divide 90 degree into 0 to 30, 30 to 60, 60 to 90, then all the way to 180. So 6 section might be sufficient. But I would like to have the data that have like as it would be in every 10 degree or 15 degree. But sometimes we have to compromise with the data. But the one that I used was I can divide it into 6 bin, meaning that I have bin for every 30 degree. It's not ideal, but well, it's workable. Maybe Dr. John have another idea.
My number was going to be 6, just like you. That was the number I was thinking. I was going to let you answer first, so I agree with that. I would just bring up what you said, quality of data, and I think what you're thinking of was fold. So we can make as many azimuthal sectors as you want, but if the fold is very small, then you're just adding noise, so it's no good. So you have to, and data regularization is very important. The pre-processing, you really want to do that. Get your data as good as you can, maybe some 5D interpolation, I don't know. But you really have to have an eye on fold. But the sweet spot number that I would have come up with is exactly the same one you came up with, 6.
Okay, I think it looks like we are quite past the scheduled for this talk. On behalf of iRocks, I would like to thank all the speakers and also all the participants who have attended this talk. Mas Budi, do you have anything for the closing?
Okay, thank you everyone, especially for our presenter, Dr. John, Mas Abdullah, Beni, and also our moderator, Allo. So it was a good discussion, a good presentation. On behalf of iRock, part of Hdi, we would like to thanks Paul, thanks our presenter and also our moderator. And until we meet again with interesting topic for the next iRock talk. For that one, maybe I conclude our discussion for today, and then hope we meet again for the next iRock talk. Good afternoon. Assalamualaikum warahmatullahi wabarakatuh.
Thanks very much for inviting me. Appreciate it. Enjoyed it very much.
Thank you.
Thank you.
Thank you, everybody.
Thank you. Thank you, John, for
Nice meeting you, John. Thanks a
being
lot.
there.
Bye-bye.